Hello, welcome to this video tutorial. My name is Johan van Pijnbroek and I'm working for the company iCare.
In this video tutorial I will give you a short technical introduction product overview about the CSI2140 for people without any technical background. So, first of all, where does the CSI2140 fits in the industry? Well, it fits in the maintenance world. Here on the right side you will see a picture of a typical plant, and normally a typical plant has thousands and thousands of rotating equipment like motors, pumps, compressor, turbines, gearboxes, conveyors and others. And just like your car, those installation requires maintenance. Now, already for many years there are 4 different concepts well known for maintenance, and those 4 concepts are reactive, preventive, predictive and proactive maintenance. Reactive maintenance means that you will never do any kind of maintenance till you have a failure on your machine. You can compare it, for example, with a light in one of the rooms of your house. Normally you're not doing really maintenance on the light installation there. When the lamp is not working anymore, you simply replace it. But for a critical machine in an installation, that is not a very smart way to do maintenance. Another example is, for example, for your car, on a regular basis you're going to the garage to do maintenance on your car. If you're doing reactive maintenance, that would mean that you will never go to the garage till your car is broken. But that will happen very often on a moment that you're not planned, that you don't want to have it. So it's a very bad moment, a very bad timing, and in an industrial environment the consequences on the production can be huge. So on important installations people don't want to do reactive maintenance. So a better way to do maintenance is called preventive maintenance, and preventive maintenance, to explain it in an easy or simple way, means simply listen to the advice of the supplier of your installations. Once again, to compare it with the car industry, you're listening to your garage, and if the garage is telling you every 20,000 kilometers you have to come in to change the oil, every 40,000 kilometers you also have to come in to replace certain belts and things like that. These are traditional examples of preventive maintenance. So that is quite popular in the industry, and normally preventive maintenance is also called time-based maintenance. You're doing maintenance based on a certain time interval, and very often the time interval is set by the supplier of the installation or based on experience. Now, despite the fact that preventive maintenance is already better than reactive maintenance, with preventive maintenance you still may see unexpected machine failures, and an unexpected machine failure can result even in a complete plant shutdown. So that is something that everybody tries to avoid. And very often you're doing also far too often and far too expensive maintenance, and we have to be very careful in the wording here. And with all the respect of people that are doing maintenance work, a very common situation is that you have a good installation. Based on the time you have to do a preventive maintenance, you do an intervention on the installation, and after the intervention you have to go over all the stored up pain with a new installation. So for that reason people are trying to do more and more predictive maintenance, and predictive maintenance means we're going to try to measure the condition of the machine, and regardless what the time indication is, as long as the machine is in a healthy condition, we will not do any kind of maintenance. Only when the first signs of a degradation of the installation are showing up, then we will plan a maintenance, and we will execute a maintenance in a proper time frame, and when also production allows it, so it's not unexpected anymore. Normally you're doing only maintenance when the installation requires really maintenance, and you reduce the number of required startups. So that is called condition-based maintenance, and we are specialized in this area. The last one, proactive maintenance, means I have a good installation, but even a good installation, I'm gonna perform certain maintenance tasks to try to improve my good installation. A traditional example here is that at a certain moment in time you decide to use better lubrication, better filtering and things like that. The main purpose is to extend the lifetime of the installation. But as mentioned before, our focus is normally predictive maintenance, so we are specialized in condition-based maintenance. Now, condition-based maintenance use several methods to measure the condition of the machine. So several technologies that can be used for predictive maintenance are vibration, oil, temperature, infrared, current, process parameters, endoscopy, visual inspections, ultrasound, thickness, and so on. But from all those technologies, without any doubt, vibration measurements is the most common used and the most popular one. Now, a key differentiator inside Emerson is that all those different technologies that you're seeing here may require different hardware, different software, but only Emerson offers all those different modules of predictive maintenance as one integrated solution and software package in the machinery health. And here you have all the different technologies and devices that we can use for that. So one of the very important one is of course the vibration measurements, and we are now coming out with a new platform for that, 4-channel analyzer called the CSI2140 Machinery Health Analyzer. So very shortly, why are we using vibration measurements and why is vibration measurements so strong? What you're seeing here is a picture of a motor, and you see the inside of the motor, and at the both sides of the motor there is a roll element bearing. This is the bearing here, and the bearing allows the shaft to be supported and to rotate as well. Roll element bearings are extremely popular, and you really have it everywhere in your world. You even have a couple of hundreds maybe at home. Everything that rotates and that needs support as well will have a roll element or sleeve bearings, but most applications are roll element bearings. A couple of examples from your house. Only in your bicycles there are already a lot of roll element bearings. Now in the industry the roll element bearings are very crucial, because if you have a damaged bearing your machine will fail completely, and maybe if your machine fails your production has to shut down. So that is a big issue for the industry. An ordinary bearing fails and they have a complete production stop. So that is something that they want to avoid, and that is why people are doing predictive maintenance and vibration measurements. But you have more than only bearing failures. You can also have imbalance, misalignment, resonance, a lot of mechanical problems on couplings, structures, lubrication problems, cavitation, and so on. Now the beauty of vibration measurements is that all those mechanical problems create a kind of a different vibration signal. Now it's up to the vibration experts to understand those patterns, and if they see the vibration signal they know, oh, this kind of vibration signal is coming from a bearing failure, so I have to replace the bearing. Or in a second case, no, this vibration signal is coming from an imbalance problem, I don't have to replace a bearing because that will not help here, I have to balance the machine. So fundamental here is to understand the vibration signals, and normally a traditional training course for basic vibration signals is already 1 2 or 3 days. I only gonna try to give you a flavor of vibration signals in a couple of seconds or minutes. Here you will see two animations. On the left side you will see an animation of an imbalance. And an imbalance, you can understand it as a rotating wheel, but because the wheel is not perfect on one side of the wheel, you have a little bit more mass than on the other side. Now, if this kind of wheels start rotating, it will create a vibration signal like this. It will create a perfect sinus, and from one minimum till the other minimum you have exactly one revolution, so one rotation of the shaft. That means in reality a typical motor is running 1500 revolutions per minute in Europe or 1800 revolutions per minute in America. Then if it has an imbalance problem, you will have 1500 or 1800 cycles like that in 1 minute of time. If we compare it with a bearing problem, you will see that the signal is completely different. The signal is completely different if you have a damaged bearing here, you have a crack in the outer race. When the machine is rotating, every time that the roll element is coming in a crack, it will create a kind of an impact. And this is how the signal will look like. Now the power of those two short animations is that everybody realize and understand immediately that two different mechanical problems create two different kind of vibration signals. In reality, we will do of course the opposite. We will measure this signal or this signal, and then it's up to the person that is doing the analysis to make the link with a mechanical problem, an imbalance or a bearing. Now the story becomes a little bit more complicated, because in reality you don't have only an imbalance, you don't have only a bearing problem. In reality you will have all those mechanical problems maybe even together in one signal. And if you have all this energy into one signal, we call it a waveform, but a waveform can be very complicated. So this can be the waveform over the time, the real vibration over the time. And what we will do now is that we will do mathematics on top of that, and it's called the Fourier transformation. And in the Fourier transformation, this complex waveform will be split into fundamental sinuses. So in multiple sinuses, and every sinus has its periodicity and its amplitude. And then we will put them in a 3D plot. And in the 3D plot, the third shaft or axis will tell you how fast a certain sinus is. So the slow speed sinus is in the beginning. If a sinus is faster, it's more to the right, and when it's very fast, it's completely at the end. Now, what is this information telling us? Remember, an imbalance was 1 sinus per revolution. That is relatively slow speed, so that will be on the left side of this axis. So this peak here is your energy coming from your imbalance. Now the bearing problem creates several impacts per revolution, so it goes faster, the energy is faster created, so it's more to the right side. Now I simplify a lot of things, so don't take this as a complete and a correct vibration theory. Once again, I simplify a lot of things, but if you simplify a lot of things, how you can understand this? This is the energy coming from your imbalance, and this is the energy coming from your bearing problem, for example. And then what we will doing is we will look to a plot like this, and that is called the spectrum. So we measure the waveform, but the analyzer will convert it into a spectrum. The benefit of a spectrum is it's telling you this is purely your imbalance energy, this is purely your bearing energy. If you have over the time an increase or a change of the vibration signal, you will see that it changed here. but it's very difficult to understand from this plot if the change is coming from an impedance or from a bearing. In the spectrum it will be relatively easy. If the energy of the impedance is increased, you will see it purely at this peak, and the energy of the bearing will remain the same. So this is a spectrum, and that is what we are analyzing most of the time in the vibration world. A short summary. Here you see a motor is generating a lot of vibration, and during the Fourier transformation it will be converted into fundamental sinuses. Every sinus has its amplitude and its periodicity, and that is represented in the spectrum. Now, to measure the vibration signal, we are working with two kinds of transducers. One transducer is called an accelerometer, and here you see a typical data sheet of an accelerometer and a drawing. It measures acceleration, but the software can integrate it into velocity or displacement. What is quite important to know is that every sensor has a certain sensitivity, and the sensitivity is a relation between the volt signal and the vibration signal. An accelerometer normally needs power from the data collector, so in the configuration you always have to specify what the sensitivity is, and you have to power it from the analyzer. On the analyzer there are a few options how to connect the accelerometer to the analyzer. On the analyzers there are two inputs, this one and this one, that can handle signals from accelerometers. So if you use only this one you have single channel, if you use this one and this one you have two channels, or if you're working with splitters, every input is now split into two, you can work with 4 sensors simultaneously. Alternatively, you can also add the 4-channel input adapter on the back of the device, and then you have 4 BNC connections for 4 accelerometers. The second kind of common use probes is called displacement probes. It measures displacement. Very common on the market are two kinds of sensitivities, 0.1 or 0.2 volts per engineering units in English systems. Those kind of sensors are normally permanently installed, and they have their own power supply. So in the configuration you have to specify the sensitivity, and normally you have to disable the power. On the analyzer you have to consider it as a volt signal, and there is on the analyzer one input for a volt signal, this one here. So if you connect it to this one, you can measure 1 volt signal. If you're working with a splitter like this, you can go to 2 volt signals. If you're using the 4-channel input adapter, you have the other side of the adapter is for 4 volt signals. Now, we are here finally at the CSI2140 machinery health analyzer. This is one analyzer with 5 main functions, and those 5 functions are analyze mode, route mode, balancing, transient or ODS model. Let's start with the analyze. What is the analyze mode? To use the CSI2140 as a standalone device and collect data. The data can be stored in a job-based structure and can be transferred to the PC. There is also a monitor mode. In the monitor mode you really convert the analyzer into a 4-channel oscilloscope, 4 channels plus tag information, so you're not really storing data, but you're looking in a kind of a live mode to the data. In the analyze mode there are a lot of predefined advanced analyze modes that you can easily start up, so to minimum the configuration that you have to do on the analyzer. However, if you want to measure a signal with a certain setup and the setup is not part of the predefined modules, there is also a module called manual analyze, and in this module you can customize really every setting that you want. So the analyze mode, as a summary, you can monitor up till 4 channels, you can configure the kind of signals, you can configure how you want to measure it, what all the settings are, and you can use it as a kind of a live mode to look to the data, or you can store the data in a job mode. The second application is called route, and without any doubt this is the most common application of the analyzer. So what is route mode? The customer will create a database on a PC. In the database you configure your areas, your machine, your measurement points, the way how you want to collect the data, your alarms, and all this information is transferred into the CSI2140 analyzer. Once in the field, you simply collect the data in a route mode. More advanced measurements can be collected and stored as well. So this is an example of the print screen of the software. So in the software you create a database. You can create several databases. In a database you can have several areas. In an area you have several machines, and in a machine you have all your measurement points. For example, in this machine, motor outboard horizontal, vertical, motor inboard horizontal, vertical, axial, the same structure at a pump, and this information is stored to the CSI2140, is transferred. And on the CSI2140 you see the name of the measurement point, the name of the machine, you install the sensor and you collect the data, and the data is stored in the analyzer. When you're back in the office, you dump all this information into the PC where you can analyze and report the data. Module number 3, balancing. What is balancing? Well, in reality, a wheel is not a perfect circle. As a result of this, the center of mass is not in the middle of the wheel, where you have the shaft position. This will create imbalance forces. Imbalance forces can create really big vibration levels. You can understand the non-perfect circle as a circle with too much mass on one side of the wheel. So correction masses on the other side will be added, and that is what you see also, for example, on your car wheels, where you see really on the wheels some small masses. Those small masses are there to correct the fact that your wheels are not perfect circles. The car is also a nice example to understand the forces. Normally, if you have big vibrations on your car, they simply balance your wheels and the vibrations are gone. Now, if you compare the size of the masses on your wheels with the total mass of your car, those masses, balancing masses, correction masses, are ridiculously small compared with your car mass. But remove it and your car starts shaking like hell. So very, very small imbalances can create already huge forces, and that is related with the speed of your car. So during a balancing job, what you have to find is the size of the mass that you need and the location where you have to add the correction mass, and that is done in a procedure that is inside the CSI2140 balancing module. Module number 4, transient. Most of the vibration measurements are collected during a stable operation of the machine in the analyze or in the route mode. So you measure the vibration signal on an installation for a short period, and after all, it doesn't matter if you take the short vibration measurement, the snapshot now or 10 minutes later or an hour later or a day later, the machine is running in a stable condition and you want to measure a short snapshot. However, certain machines operate in an always changing mode, like certain batch processes or elevators or startups or shutdowns of a machine. Now, If the conditions are changing all the time, we are calling that a transient event. And during a transient event, it is not sufficient to collect a snapshot of the vibration signal. What you need here is a full raw signal during the transient event. In other words, your CSI2140 is now converted into a digital tape recorder. Advanced signal processing can be done afterwards in the software. So afterwards in the software, from any moment in time of your transient event, you can calculate the spectra, the waveforms, you can see the full transient data, you see speed plots, orbits, waterfall plots, both Nyquist and many others. The software even provides a replay mode to look live again to the transient data. And the last module is called ODS model. What are you doing in the ODS model? First of all, on the software in the PC, you create a wireframe of the installation. What you're seeing here is a structure and the motor of a fan. So we call this a wireframe that is created on the PC. Then you install on one location one sensor, and during the complete measurement campaign you keep the sensor at this location, for example here. Then you have a second sensor, and the second sensor is installed one after the other on all the points of your wireframe, but not only installed in one direction, you have to install it in the three directions, and for every position you will always measure the relationship between the vibration here, your fixed sensor, and your walking sensor. If you do that for all the points and you transfer the data to the PC, all the data is linked into the wireframe. And then in the software you can animate the wireframe, and here you see an example of an animated wireframe, and this is an extremely strong analysis tool to find structural problems. Now, for order administration, in the past we were always working with separate part numbers, but now there are so many different options and combinations that for order administration for the CSI2140 we will work with a model string. So in a model string there is first of all a kind of a part number for the portable vibration analyzer called A2140. Then you have to add a 1, a 2 or a 4 depending on the number of channels that you want. Then you have to add R, A, C or 9 depending on the standard downloadables that you want to have on the analyzer. Purely root is R, purely analyze is A, and C is root, analyze and cascade. 9 is when you don't want to have those standard periodic vibration analysis downloadable programs. If you want to have balancing, you have to add a B. If you don't want to have balancing, add a 9. For the advanced vibration analysis downloadables, add a T for transient, an M for ODS model, or a G for transient and ODS model, a 9 for none. Then there are the codes for the different languages: English, Spanish, French, German, Turkish, Swedish, Finnish, Chinese, Russian or Portuguese. Add key L if you need hazardous environment certification, and A when none. If you want to have the unit with Wi-Fi and Bluetooth communication, add a double U. This is used for two things. It's used for communication to the PC, so to dump or to load data, or to talk with devices like Bluetooth headphones, for example. Add 9 if you don't need wireless communication options. And then there are 3 more options. E if the customer also wants an external battery charger and spare battery. H if he wants a hard side carry case, and K if he needs a 4-channel accessory kit. So here is an example of a string. So it starts always with A2140. If you need 4 channels, add a 4. If you need root analyze cascade, add a C. If you don't need balancing, add a 9. If you don't need advanced vibration downloadables, add a 9. Then specify the language, in this case EN for English. Then add NA when no hazardous environment certification is required. Add a 9 when no wireless is required. And E if you want to have the spare battery. H the hard side carry case.
We are now at the end of this video tutorial. Thank you for watching this tutorial. For more information about iCare and our products, please visit our website or drop an email to one of the following emails. Thank you, have a nice day.